Hello and welcome back to Statistics 1. This is the last section of Chapter 6. Nope, Chapter 4. It's Section 6. There we go. I know there's a 6 somewhere. Multiplication rule and independence. We are going to take a look at first the definition of the formula for the general multiplication rule. And it says, if A and B are any two events, then probability of A and B is given with a probability of A times probability of B given A. This is just the formula we had before flipped around. (17) female, 23, and this is the class of 40. So 40 students in a classroom. So we have a frequency distribution table, right? That's the frequency. I guess G for gender, whatever. So now it says two students are selected at random from the class. The first student selected is not returned to the class for a possible reselection. So this is the part when we go without replacement. What is the sampling without replacement, right? So find the probability that the first student selected is female and the second one is male. So we are looking for probability that the first student is female and second one is male. So this is what we are looking for. All right. Now what do we have here? You want the probability of female student. Well, we have 40 students, 23 are female, so 23 out of 40. Well, actually, let me first write the formula. So that's going to be P of F times probability of B given A. So B given A, that's probability of Really? Male given female? Really? Same thing? Can you pick a female out of a set of 30 male? Oh no? Okay. So it's actually the 40 that you have to worry about, right? The total, exactly. Now, remember that we already picked a female in the first one and we said no replacement. Therefore, now you don't have 40 people to pick from, you have 39, right? So you are trying to pick a male given 39 people. Now that's a total. So, when we are picking a female, so look at a classroom over here, right? To pick a female, we have a frequency distribution, so amount of females in a class, everyone in a class, so that's going to be simply 23 over 40, right? Probability here. But then, that one female is picked, right? Kick her out for a moment, right? Don't panic yet. Kick her out, right? And then now we have 39 students in a classroom, right? And now what is the probability to pick male from there? Well, 17 again, right? So But my question is, how about to pick another female? 22, we kicked one out, right? Because she was chosen, she was picked, right? Great, wait outside. Now we have 22 females in the classroom, right? And then if it's 3 female, okay, great. Then 21, 20. So that's without replacement, right? So, you know, there is some thinking that has to be utilized here. So we have to pick the first female, probability is 23 over 40. Times, and now to pick a male, we still have 17, but now there is 39 people in the room. And you compute this in your calculator, and that will be overall probability to pick them exactly. It's not easy to pick. Remember, because if you're picking randomly, you can pick female, female. You can pick male, male. You can pick female, male, which is what you're looking for. You can also pick male, female, right? So it's not easy, and these probabilities shouldn't be.
Yeah, I got the point.
Because I figured that was.
It's 06.
Easier.
Yeah.
Yeah. So 0.2507.
Yes, 0.251. 251, yes.
Oh. 6. That was like
All right. So
Did I put 6 there?
0.251, so it's 25%. Okay. But you want us to round, so we'll say 25%.
It's 25.1%. Which you can't really tell because this one is curved. It's really curved. This is a pretzel one. Okay?
Maybe that's a percent.
It's a pretzel one. That's what it is. That one looks like. I mean, it looks fine on a tablet. It's the programming. I think curves it into a pretzel over there.
Oh, he thinks.
No, the internet died, so it's not updating again. You know what? This class is good for 15 minutes, and then everything dies. So we might have to move to like arts building or something where stuff works. So stream is out again, and there we go, adjusted. All right, now so that was A. Let's practice more. Part B. What is the probability of picking a female and another female? Again, without replacement. So you pick a female, kick that person out. We have the rest too.
So, pick female and female.
So that's going to be probability of a female times probability of the female given 39.
Yeah, so 23 over 40 times 22 over 39.
Nice. And that is going to give us again some numbers. No, I'm serious. All right, let's pick probability of a male and female what it changes.
17 over 40.
17 over 4, so that's probability of a male times probability of the
And then 23 over 39.
female given 39. Good. 17 over 40. 39. Good. What do we have?
But I'm not bringing
Yeah, that's a shame. Now let's take a look at a tree diagram for this. Waited a whole semester to use green. It's appropriate now for the tree diagram. Right. All right, so let's take a look at these probabilities. We're going to start where we have everyone on the pile, right? Say it's all. And then there will be a probability to pick a female first, and probability to pick a male first. And probabilities are 17 over 40 and 23 over 40. So those are associated probabilities. Now, once you pick your first student, whether it's male or female, you have to pick the second one. Now that is going to branch off of what ones you already have. So now, to pick another female, or to pick a male, or to pick a female, or to pick a male. So F1 and M1, that one stands for the first draw, right? And then F2, M2 stands for the second draw. Now, what are the probabilities? Well, if you are going along this branch, right, you already picked a female, you are going into the next branch, you have one female less and one person less because, well, that female was a person, right? So everything goes down. Number of females by one and number of people by one because one person was chosen. Remember, we picked her outside the classroom. So now the next person is going to be 22 out of 40. That's what I said. 22 out of 39, yes. I would tell you to, just go back to the stream and listen to it, but it's down, so you can never win. And picking a male, we still have 17 male, but it's 39 people. Now we're going to take a look at the branch for male. If you pick the male first at 17 over 40, then to pick a female, you still have 23 over 39, and male will be 16 over 39. Very good. So now this gives you just a basic simple multiplication around, will give you immediately probabilities. This is probability of female and male. This is female and female. This is the probability female and male. This is the probability of male and female. And this is the probability of male and male. So, to find those probabilities, you just need to multiply on the branch. Multiply this way, multiply that way, this way, that way, and the numbers go over there. It's really cool. Now, two events are independent, right? If events, so event B is said to be independent of event A if the probability of B given A is the same as probability of B. We'll take a look into the details there. So event B is dependent of event A if probability of B given A is the same as probability of B. I don't know if this makes sense. To me it does, because we see that event A doesn't matter in this case, so B is going to do its own thing. But let's take a look at some examples to make sure that this makes sense. So, playing cards. So we're going to, again, take a look at the deck. And we're going to define some events. So F is event that face is selected. K is king is selected. And age is that heart is selected. So these are the three events. Let's list their probabilities. For face, remember ace is not a face in the deck for the way the book defines it. So how many face cards do we have total? How many face cards per? 12. Because we're not taking ace, right? So I actually know a game where ace, 10, jack, right, are also, so ace and 10 are also counted as face cards. So I know a game, they used to play that as a kid. So we are only using jack, queen, and king as face, and then you have 4 suits, 3 times 4 is 12. So probability of face is 12 over 52. I'm not going to reduce any of these probabilities because we might need common denominator and so on. What is the probability that king is selected? 4 over 52, very good, because there are 4 kings, right? 2 black, 2 red. Each suit has exactly 1 king, so there are 4 suits, 4 kings, 4, 52. And then heart is selected.
13.
Very good, 13 hearts. Great, no coughing. So, we have our probabilities for the basic stuff. This is what we did this on day 1 for probability last week. So determine whether the event K is independent of F. So is K independent of F? And B, is K independent of H? Parts. So is picking a king independent of picking a face?
Yeah.
No.
So the answer is no. Okay, we move to the next lecture then. Good. So we have the formula, right? And we want to see if picking a king is independent from picking a face. So what are we supposed to check? We are supposed to check the probability of king given face needs to be the same as probability of getting a king. So this is what we need, right? Need this to be true to have independence. Right? So let's calculate probability of king given face. Probability of king given face cards is what? How many face cards do you have? 12. How many of those are kings? 4. So the probability works out to be 1/3, right? And what's probability of a king? Which is 1/13. Is 1/13 and 1/3 the same thing? Nope. Maybe. So are these events independent?
Yes.
No. Because these numbers have to be the same if they are independent, but they're not. All right, so the answer is no.
Yeah, wouldn't it be like, I would imagine like, if they were independent, they would be different. If they're independent, they're the same.
No. If you're independent, you have to be the same as someone who provides for you. Like, think of a 5-year-old kid.
Like, you have to be able to be in your own thing. Does it make sense when you say it?
Then you rethought of it. And now it doesn't. So is picking a king independent from picking a face? No, it's dependent because every king is a face. So they can't be independent. Picking a 7 should be independent from face, right? Because no 7 is a face. So there is some heavy-duty thinking that you have to put into these things. Let's take a look at B. If probability of what do we need? Picking a king out of heart, so given hearts, is the same as picking a king. So probability of king out of hearts, there is a 1 in 13. Because, well, actually, let's just write everything. So there are 4 kings, and there are 13 hearts, right? There are 4 kings. No. There is, no, given hearts. There is 1 king. Sorry. There's 1 king given hearts. Remember what's given to you, right? I am giving you only hearts. That's only 13 cards and only 1 king in those 13. There's only 1 king of hearts. You don't have 2 or 3 kings of hearts. So 1 out of 13 cards. That's the probability of picking. If I give you only the hearts from the deck, you only have 1 king in that. That's a quarter of the deck, right? So 1 in a 13. And what is the probability of picking a king in general? Which is 4/52, which is also 1/13. Now they're the same. So they're independent. Yes. So, is picking a king independent from picking a face? No, because every king is a face. It can be independent, right? Now, is picking a king independent from picking a heart? Yes, because not every heart is a king. Not every heart is a king, right? You have a 7 of a heart, right? So independent. Good.
Is this kind of like the mutually exclusive thing?
I'm sorry?
Is this kind of like the mutually exclusive?
It's similar but not the same.
So, but like in regards to that, if it was mutually exclusive, like the king and the face, would that?
But they're not mutually exclusive, right? See, that's the part. Mutually exclusive means that 2 events cannot occur at the same time, but not that they are actually shared events. You see, mutually exclusive. What would a mutually exclusive be? It's raining or it's not raining, right? So sunny or rainy. You can toss in another ring, snow, right? So you have all of those to be mutually exclusive. It's like a non-equal terms, like okay, rain, snow, sunny, snow, rain, rain. You turn the knob. So it's one or the other, or heads and tails, right? You put the coin, heads and tails, right? But the independence is where you can have certain qualities that are later, right? So a card could be a heart and a king, right? And that's where the independence comes in. So there are mutually exclusive events, which is if you pick a black card, it's not red. That's mutually exclusive, right? But you can't talk about mutually exclusive between a king and a red because you have a red king. You also have a black king, but you also have a red king, right? So the independence and mutually exclusive are not the same. They deal with different situations. But that's actually a very good question and a very good link that you are trying to make. Yes?
So it's kind of like they're independent if they have the same probability.
Yes, which is what the red.
Which is kind of confusing. It's like they're the same, but
The event independent doesn't mean the same. So that's
that's what's that's why it's confusing.
Why is it confused?
Because
because they're equal, so you want the same.
I
Okay.
think of independent, I think like separate, like they're independent of each other. Not,
Yes.
Yes. That's why it's like difficult to think like they're independent if both have the same probability. I'm thinking of it.
But that's exactly what it. See, look. When you are independent, so let's pick a child and a parent. Child is dependent on the parent for parent to provide, or guardian, or uncle doesn't, right? Okay. So child is dependent on that. Are they the same? They're not the same, right? Now, when child becomes independent, are they the same now? This one provides for himself, this one provides for himself. The same. Yes, I see.
That's weird. Yeah.
I know. This is where the thinking comes in, right? And processing information, or trying to find a better example to make sense of these things. In general, I mean, but I'm glad that, the first step is to think through the examples that are there. So now, guys, if the events are independent, then we can just multiply probabilities. If the events are independent, we can just multiply probability. So probability of A and B is just probability of A times probability of B.
We'll make it a smaller than it is independent.
Yeah, they make it smaller. Every time you multiply, it makes it smaller. Yeah, it's harder. It's harder to pick exactly what you want, right? You remember the difference when I said when someone gets pulled over, it's license and registration and proof of insurance. Now, you have no choice. It would be much easier if it was license or registration or proof of insurance, and then whatever you come up with is good, right? If you give all three, still good, right? So it's much easier to deal with or, right? Give me a pencil, right? You need to borrow a pencil or a pen or something, or anything to write with. So you have options if you're not picky, but it's not that really. Give me a. Can I have a pencil? Right? Pencil. All right. That's it. Right? Pencil. And now you really want to be picky. You need pen and pencil. Right? Pen and pencil. So now someone has to scramble. What happens if I have only 10 pencils? I don't have 10. Right? That's how I used to roll. I never had the pen. So I always said I still have to borrow the pen. I have the one that doesn't dispense ink over there. I love it. I go to a meeting. So can I sign this quick? I don't explain. Sure. Let them figure it out. Like it's invisible ink, okay? So now you take the document, put it above the fire, right? And it should reveal the signature. I know. Invisible ink. Scroll back real quick. Sure. That was real quick.
So after is K independent of F and is K independent of H.
Wow, you just said real quick. I mean, so exactly. That's the rest of the problem.
Thank you.
All right, you're welcome. See, it's the service over here. So now, make sure you are catching those important words. Let's see. And now, special multiplication rule can be extended to any number of events, right? So you just multiply the probability. So what is the probability that it's going to rain today, and that I'm going to have a yellow shirt on, and that I'm going to feed the fish, and I'm going to, right? So when you look at these things, right, the probability that it's going to rain today, I'm going to look up online, right? They say rain 40%. Great. So I have 0.4 there. Probability I'm going to have yellow shirt. Perfect. So what do? I go and count all of the shirts I have and say, okay, 3 of those are yellow. So probability, right, of that, and I have probability of yellow shirt. Probability that I'm going to feed the fish. Well, that's a little bit harder, because first I need to know how much I like the fish, right? If I like it very much, most likely I'll be feeding the fish the proper way, right? Which is whatever amount is necessary for that fish, and then I will look at the calendar, is that the day? If I don't like the fish, probability of feeding the fish is 0, right? Because you want to get rid of the fish. So there is going to be always a logical way to determine the probability, and it is only, that probability is only stopped, blocked, whatever, by our ability to take into account all possible outcomes in a sample space to figure out what the probability is. There is a probability that says that someone is going to get in a car accident. There is a probability that shows that being at the airplane is much safer than being at a car, I think 27 times or more. Yeah, sure, when an airplane drops out of the sky, 300 people die in one shot. Yeah, but when you consider that about 30,000 just Americans die in a car every year, well, 1 or 2, well, I don't even know when was the last plane that fell and had all 300 people die. I don't remember, really I don't remember. But I know that the statistic of every year that it's published, right, is that 30,000 Americans die in car accidents, right? For me, who understands probability very well, it's very interesting to see how uneducated and simple-minded media is. And then, obviously, the public follows that. The Tesla self-driving, so I know of 3 accidents. And also the autonomous driving and how much people are not a fan of having computers drive, where the statistics clearly shows that that is actually the best possible thing, because there will be the least amounts of deaths, right? And people will say, well, you know what? You heard it, that person died because the computer made a mistake. I say, yeah, so what? A person died. Okay, let's let 100 people die because of that. We have 30,000 dying now because the computer is not driving. So let's take those odds, right? So if you have a global network, right, of something like that, like autonomous driving, when you look at it, you will have no traffic. You can go dead drunk anywhere you want to go because you're not in a control. You can get a ticket because your car can't drink. All right. So these are but there is so much that gets fixed by, you can be the best driver ever, most experienced driver ever, not cause any accident for 50 years, never drink, never do anything stupid like reading newspapers or changing pants while you're driving, and people do that. I observed a truck driver, those 18-wheeler huge ones, right? He had a map, all right? Now, granted, this is 10 years ago, but still, a map blocking everything, right? You can't stop, right? So, you know, these things, and when you look at the probability, you understand, right? What are the good odds, what are the bad odds, and if you can predict all of the outcomes, as I said, you would have the true probability for the event happening or event not happening. And believe it or not, everything that is around us is just a probability, right? Of you know, going all the way down to particle physics and so on. It's all probability driven. So now we have the independence and this special rule. And your question regarding the mutually exclusive versus independent events has one paragraph at the end which says the terms mutually exclusive and independent refer to different concepts. Mutually exclusive events are those that cannot occur simultaneously. Independent events are those for which the occurrence of some does not affect of the probabilities of others occurring. And that is what I said earlier. Me feeding the fish doesn't at all, like the probability of me feeding the fish doesn't impact the probability of whether it's going to rain or not. Right? So, but then you have the linked probabilities where the events would be dependent because it matters what you do in one case and not in the other. So if I'm going to have an umbrella that's driven by probability that's going to rain. So if I see that probability for the rain is high, then probability of me bringing umbrella is high as well, and those are dependent. Because as soon as the probability of rain drops down to, let's say, 30% or 20% or whatever, I'm just going to say, well, I'm not bringing umbrella. I still have a choice of bringing it, but I'm making the one. So probability is that I will not bring the umbrella. So one probability is tied to the other probability. The outcome of one depends on the outcome of the other. And that's what the independence is, where the mutually exclusive events are two events that cannot happen at the same time, like heads and tails. They both have probability of the half. When you add those two probabilities, you get one. Those are all possible outcomes, and then they're mutually exclusive. Now, flipping a coin number of times are independent events, because flipping a coin on the first run and flipping a coin again, well, the probability is still half, half, and half, and half, and half, and half, right? Every time. But picking a card and not putting that card back and then picking another card, those are dependent events. Because something that you guys will, with practice, with homework, like with both problems that you have to do for homework, will practice until you understand it very well. Or 3, yeah. Sometimes I know it. Sometimes they assign 3. I've seen it. So, one more problem from the textbook to practice this, and then we are going to move to 5.1, which is a short section with some details. So this is problem 4.184. And it talks about governors. The National Governors Association publishes data on U.S. governors, and so and so and so. And this is data for 2013 governors. We have the frequency distribution table. So party and the frequency. We have Democrats at 20 governors and Republicans at 30 governors. So these are the governors in 2013. Let's take a look at some probabilities. First of all, you might want to immediately have the total number of governors, which is 50 governors. Find the probability that the first is a Republican and the second is a Democrat. So we are picking a probability that the first chosen governor is Republican and then Democrat. Great. So what is the probability of picking a Republican? 30 out of 50. All right, so you picked your Republican, and now kick it out of the office or the classroom or whatever. Now you want to pick a Democrat. 20 over 49. Now in this case, you can cancel these zeros, right? So you have 60 over 245. So you can calculate the odds of picking exactly Republican and the Democrat, Republican being first. Find the probability that both are Republicans. So probability of R and R. So what is the Republican and a Republican? Nice. So we start with 30 Republicans out of 50 people. Times, we pick the Republican, so kick the Republican out and one person, right? Because that's a Republican, that's a person. So kick out, so that's 29 over 49. And you can calculate those odds. Great. Part C. Draw the tree diagram for this problem similar to one shown. So tree diagram. Okay, that's green. Tree. We are starting with 50 people. And we are going to pick a Republican first or a Democrat in a first draw. What is the probability to pick a Republican? We already know. 30 over 50, so we'll call that 3/5. And to pick a Democrat is 2/5. Now each one of these will branch into the second round where you get to pick a Republican 2 or a Democrat 2 or a Republican 2 or a Democrat 2. So that's the second round of picking that we get to do. So now if we are picking a Republican and then another Republican, remember that both numbers go down. So that's going to be what we had, which is 29 over 49. But if you want to pick a Republican then Democrat, then the number of Democrats, since we picked a Republican in the first draw, the number of Democrats stays 20 over 49. Well, we picked our first Democrat. So now we are going to pick a Republican. Well, number of Republicans is still 30, but we have 49 people to choose from. And if we pick the Democrat first, and then we want the Democrat again, that's going to drop down to 19 over 49. And these are all possible probabilities. What was the part B? Did anyone compute 0 point? No? Who cares? Yeah, I know. It's just math, numbers, boring. 0.355. Good. Thank you. Now, actually, let's compute all of the probabilities in a tree. So what is the Republican? That's going to be 3/5 times 29 over 49. What do we get? So 0.355. Oh no, that was Republican. Good, I had the number. What else? What are the other ones?
That's 0.244.
Okay. They have to be the same.
Yeah, I didn't know when I did my answer. I didn't know that.
But is it 4-4 or 4-5?
4-5.
4-5 for both, okay. And now to get the one on the bottom. 0175? 155?
That's 205, right?
That's 205, yes. 1.55? $0.155. We need all of these probabilities because for D, they're asking what is the probability that the two governors selected have the same political party affiliation. So pick two from the same party. How would you go about that?
Follow the top of the tree line here, the R1
Okay.
goes to motion, goes back.
Mm-mm.
And then you would do the same for Democrat and Arab too.
Yes. But what do you do with that? So, yes, you were right that we have to use this and we have to use this, right? Fine. But what do I do? So when I follow these two paths, I end up with this and this.
Those are your chances of 9.52 for the same party.
Yeah, but I need how do I combine these? Add them. Very good. Because it's or. You see, they didn't ask you exactly, right? They say, what is the probability that the two governors selected have the same political affiliation? You win whether you pick Republican, or Democrat, right? And the or is addition. So you simply add these guys. So you add them. For part D, it will be 0.355 plus 0.155. That gives you what? 0.51, right? Note that the other two in the middle are 0.49 and then they all add to a 1, right? Yeah, good. Well, that's the next question, E. Different. So pick two from different party. And that would be 0.245 plus 0.245, which is 0.49 in this case. Cool. So this was a problem 184. There are many other problems that you guys can enjoy. Medical school faculty gives you the gender and ranks. Class levels, freshman, sophomore, junior, senior in the school. Gender and working from home, I think. Flipping the coin. More Republicans and Democrats. Social science, psychology, male, female, I guess that's the distribution, who takes what, and so on. So there's a lot of these things that you can try. All right, well, that's it for this lecture. We're going to restart and briefly go through 5.1 to introduce all the terms that you need to know. We have 17 minutes left.